Welcome back, children. Through this video, I will teach you about modern periodic law, structural features of the long form of periodic table, and I will also tell you how to name the elements with atomic number greater than 100. In 1869, Mendeleev proposed his periodic law, which states that the properties of the elements are periodic functions of their atomic weights. He developed a periodic table based on his predictions at a time when chemists knew nothing about the internal structure of atoms. In 1912, Henry Moseley, a young English physicist, conducted experiments in which he bombarded 38 different elements with high-speed electrons and measured the frequencies of X-rays emitted by them. When he plotted the square root of frequencies of the prominent X-ray lines emitted by elements against their atomic numbers, he got a straight line which is shown in the graph displayed. This led Moseley to conclude that atomic number was a better fundamental property of elements instead of atomic weights, and therefore he suggested that atomic number should be the basis of classification of elements. Thus, Henry Moseley proposed the modern periodic law, which states that the physical and chemical properties of the elements are periodic functions of their atomic numbers. Students, let's get acquainted with the present form of periodic table. Numerous forms of periodic table have been developed from time to time, of which some forms emphasized on chemical reactions and valence, while other forms stressed on the electronic configuration of elements. Of these, a modern version which is used widely and conveniently these days is called the long form of the periodic table. This periodic table is constructed on the basis of the modern periodic law. It is also called Bohr's table since it follows Bohr's scheme for the arrangement of various electrons around the nucleus. Let us learn about the structural features of the modern periodic table or the long form of periodic table. In the periodic table, the elements are arranged in horizontal rows called periods and vertical columns called groups. And do note that if we closely study the way in which these elements are arranged in a period or in a group, we can find that they are arranged in the increasing order of their atomic numbers. Now look at the first group. Look at lithium, its atomic number is 3. Look at sodium, its atomic number is 11. Potassium, its atomic number is 19. Rubidium, its atomic number is 37. So if we take the elements in a group, we can find that they are arranged in the increasing order of their atomic numbers. Similarly, look at period number 2. Look at the second period. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Look at their atomic numbers. Lithium is 3, beryllium, the atomic number is 4, the atomic number of boron is 5, the atomic number of carbon is 6. So elements in period are also arranged in the increasing order of their atomic numbers. Groups are also called families. Elements having similar outer electronic configurations in their atoms are arranged in vertical columns. Now look at the first vertical column. The elements lithium to francium have similar outer electronic configuration, right? That is, in lithium it is 2s1, in sodium it is 3s1, in potassium it is 4s1, in rubidium it is 5s1, in cesium it is 6s1, and in francium it is 7s1. Since they have similar outer electronic configuration, they are arranged in a vertical column called group. They constitute a family of elements with similar properties. Clear? Now with this, what do you understand? Elements with similar outer electronic configuration constituting a group exhibit similar properties. Now there are 18 vertical columns called groups in the periodic table. Now how do we number these groups? Groups are numbered from 1 to 18 according to the recommendation of International Union of Pure and Applied Chemistry. In short, I would call it IUPAC. Earlier, in olden times, groups 1 to 18 were designated as 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8, 1b, 2b, 3b, 4b, 5b, 6b, 7b and 0. Okay, however, in the we can find both systems of numbering of groups in the present form of periodic table. Okay, this you can see in the long form of periodic table just below the present designation given to groups. That is, you can see them under the numbers 1 to 18. Now, what about periods? There are 7 periods in the long form of the periodic table, and these are numbered as 1, 2, 3, 4, 5, 6 and 7 from top to bottom of the periodic table. Now, look at the outer shell electronic configuration of lithium. It is 2s1. The number 2 before s1 corresponds to the number of the outermost shell into which the last electron enters. So in the case of lithium, the last electron enters into the second shell. Therefore, the corresponding value of principal quantum number n is 2. This is the highest principal quantum number possible for lithium in its ground state. If we consider neon, this is the last element in the second period, isn't it? It has an outer shell electronic configuration of 2s2, 2p6. Therefore, the value of n, that is principal quantum number, is 2. So, the highest principal quantum number possible for neon again is 2. Now, let us consider potassium. Okay, it is the first element in the fourth period. Now, what is its outer shell electronic configuration? It is 4s1. So, the value of principal quantum number n here is 4. So, the highest principal quantum number possible for potassium is 4. Let us consider krypton. This is the last element in the fourth period. Okay, it has an outer shell electronic configuration of 4s2, 4p6 and the value of principal quantum number n for krypton is 4. So, the highest principal quantum number possible for krypton is 4 in its ground state. Clear? Hence, all elements with the same principal quantum number in their outermost shell are arranged in the same row or period. Okay, now if we take the elements of the second period, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, all of them have the same principal quantum number, that is n is equal to 2 in their outermost shell. Consequently, the period corresponding to these elements are then numbered as 2. Similarly, if we take elements in period number 4, that is starting from potassium, its atomic number is 19. Potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine and krypton. Their outermost electronic configuration has the same principal quantum number n, which is 4. Consequently, the period corresponding to these elements are numbered as 4. Clear? So, in general, the period number corresponds to the highest principal quantum number n of the elements in the period. Now, how many elements are there in each of these 7 periods? The first period consists of 2 elements. The second and third period consist of 8 elements each. The fourth and fifth period consist of 18 elements each. The sixth and seventh period would have a theoretical maximum of 32 elements on the basis of quantum numbers. Also, 14 elements of sixth period called lanthanoids. Okay, lanthanoids are also called lanthanides. Okay, Nides. That would be the spelling then. Okay, so 14 elements of 6th period called lanthanoids and 14 elements of 7th period called actinoids or actinides are placed in separate panels at the bottom. With this introduction on periodic table, let me now explain how elements with atomic number above 100 are named. About 118 elements have been identified till date. Although names and symbols to many of these elements have been assigned, these are still not universally accepted. Usually, elements with atomic number greater than 100 are named by their discoverers. The names suggested by the discoverers are then approved by the International Union of Pure and Applied Chemistry. At times, scientists get tempted to claim credit for the discovery of the new element even before collecting reliable data on it. For example, both American and Soviet scientists claimed credit for discovering the element with atomic number 104. While the Americans named it Rutherfordium, the Soviets named it Kurkatovium. To overcome these difficulties, the International Union of Pure and Applied Chemistry, IUPAC in short, they recommended a systematic nomenclature for naming elements with atomic number greater than 100 till their names are officially announced. Well, how do we name those elements as per the recommendations of International Union of Pure and Applied Chemistry? Let's see. The IUPAC names are derived directly from the atomic numbers using numerical roots for 0 and numbers 1 to 9. Now look at the table. The root for 0 is nil. The root for 1 is un, okay? The root for 2 is bi. The root for 3 is tri, and so on. And the root for 9 is ENN, N. Okay, usually students go wrong when they write the root for the number 9. Okay, it is ENN, N. Clear? The roots are linked together in the order of digits which make up the atomic number, and the suffix IUM is added at the end in order to write the IUPAC name of the elements with the atomic number greater than 100. Suppose we need to write the IUPAC name of the element 102. Okay, atomic number of the element is 102. We know that the roots corresponding to 1, 0 and 2 are un, nil and bi respectively. So the roots are linked together in the order of digits which make up the atomic number 102, and the suffix IUM is added at the end. So IUPAC name of the element 102 is given by un plus nil plus bi plus IUM, which is equal to un nil bi m. Note that the IUPAC name of the element 102 has only one I between bi and IUM. Okay. In certain cases, the IUPAC names are shortened. For example, when we tried to write the IUPAC name of the element 102, we noticed the root bi and the suffix IUM. Didn't we? If they were linked together, we would have had UNNILBIIUM with two I's as the IUPAC name. But it's not so. One of the two I's are discarded, and hence the correct IUPAC name is UNNILBIIUM. Clear? We can also see that the root tri and the suffix IUM is shortened and written as trium, TRIUM. So this is how we write the IUPAC names of elements with atomic numbers greater than 100. Now, how to write the symbol of the element 102? For example, the symbol of the element 102 is obtained from the first letter of the roots of numbers which make up the atomic number 102. Now look at the table. The first letter of the root un of the number 1 is U. The first letter of the root nil of the number 0 is N. The first letter of the root bi of the number 2 is B. So on linking, we get UNB as the symbol of the element. Hope you are clear. So this is how we write the symbol of the element with atomic number greater than 100. Students, let's now try to write the IUPAC names and symbols of a few elements with atomic number greater than 100. Let's see example 1. What is the IUPAC name and symbol of the element with atomic number 112? We know the root for 1 is un. Again, the root for 1 is un. The root for 2 is bi. On linking these roots and on adding the suffix IUM, we write the IUPAC name of the element 112 as un by m. You can see that we have shortened the root by and the suffix IUM when we linked them together as BIUM, B-I-U-M, okay? So it is not B-I-I-U-M, but the correct way of linking is B-I-U-M. Its corresponding symbol is written by linking the first letters of the roots un, and by in the same order as UUB. Therefore, UUB is the symbol of the element 112. Now, what is the IUPAC name and symbol of the element with atomic number 114? The root for 1 is un. Again, the root for 1 is un. The root for 4 is quad. On linking these roots and on adding the suffix IUM, we write the IUPAC name of the element 114 as un and quadium. Its corresponding symbol is written by linking the first letters of the roots un, and quad in the same order as UUQ. Therefore, UUQ is the symbol of the element 114. Now, the last example. What is the IUPAC name and symbol of the element with atomic number 120? The root for 1 is un. The root for 2 is by. And the root for 0 is nil. On linking these roots and on adding the suffix IUM, we write the IUPAC name of the element 120 as un by nilium. Its corresponding symbol is written by linking the first letter of the roots un, by and nil in the same order as UBN. Therefore, UBN is the symbol of the element 120. Thus, a new element first gets a temporary name with symbol consisting of 3 letters. That is what you learned to write just now. Later, permanent name and symbol are given by a vote of IUPAC representatives from each country. The permanent name might reflect the country or state of the country in which the element was discovered or pay tribute to a notable scientist. As of now, elements with atomic numbers up to 118 have been discovered. Official names of all elements have been announced by IUPAC. This table shows the IUPAC nomenclature of elements with atomic number above 100. Students, do practice writing the IUPAC names of these elements using roots and their corresponding symbols. That is what is required from you at this stage. So children, through this video, I hope that you have understood modern periodic law, structural features of the long form of periodic table, and the IUPAC nomenclature of elements with atomic numbers above 100. Thank you all for your patience in listening.